An object the size of a city moving through space at 32 kilometers per second defies the laws of physics. It's an interstellar traveler, tracing a hyperbolic path that will never orbit our sun. Resembling a comet, it vents gas that forms a glowing tail stretching over 500,000 kilometers, yet remains steadfastly on course, undisturbed by distant stars' gravity. Astronomers have never seen anything like it, and its origins remain a mystery. Could this be our first encounter with extraterrestrial technology, a vessel crafted by intelligent beings from another star system? So before we go deeper, hit like, subscribe, and tell me in the comments what you think this really means. And if you want to help this message reach others who still wonder, share it. On X, Facebook, Reddit, or even just in your group chats. You're the reason this search is alive. Thank you for keeping your eyes open. First spotted in 2019 by Hawaii's Asteroid Terrestrial Impact Last Alert System, Atlas. The object, named 3I Atlas, appeared as a faint streak in the night sky. Observations revealed a roughly 120-meter wide object, either cigar-shaped or pancake-like, with a surface darker than charcoal, reflecting less than 10% of light. This film explores the truth about 3I Atlas, an interstellar visitor challenging our understanding of the universe. It's not just a story about a comet. It's a reflection on our place in the cosmos and the possibility of extraterrestrial life. As we uncover the mysteries of this interstellar interloper, we confront timeless questions. Are we alone in the universe? Or are there others observing us, hinted at by this enigmatic object's silent passage? 3I Atlas may offer answers or remain a cosmic enigma, but its presence underscores the universe's vastness and limitless possibilities. Its journey reminds us that the cosmos is stranger and more wondrous than we can imagine. Part 1. The Impossible Object. Why is 3I Atlas breaking the rules of the cosmos? Imagine holding a garden hose while trying to hover perfectly still. Physics says it's impossible. The water's momentum should send you tumbling. Yet, 3I Atlas, an object the size of a city block, is doing exactly that in the darkness between worlds. It's venting material like any normal comet, but somehow avoiding the acceleration that should inevitably follow. This is not a glitch in the data. This is a cosmic anomaly that could rewrite our understanding of the universe. Observations confirm that 3I Atlas is actively venting gas and dust, creating a shimmering coma visible to the Hubble Space Telescope. The coma, a glowing cloud of ejected material, stretches over 100,000 kilometers into space, a spectral halo caught in the faint light of distant stars. Yet, when astronomers calculate its trajectory, they find something extraordinary. The non-gravitational acceleration, the push from escaping gas, is stubbornly absent. This isn't just unusual, it's unprecedented. It's as if the object is defying one of the most fundamental principles of spaceflight. To understand the scale of this mystery, consider the numbers. A typical comet might lose up to 10 tons of material per second during its closest approach to the Sun. This violent outgassing creates a visible tail millions of kilometers long and alters the comet's trajectory. But 3I Atlas, despite venting at a comparable rate, shows no measurable change in its path. Its movement remains as predictable as a clockwork mechanism, defying the chaotic behavior expected of such an active object. The laws of physics seem to bend around it, leaving scientists to question whether they're witnessing a phenomenon never before observed. Two interpretations emerge from this puzzle. The first suggests natural explanations, a massive nucleus absorbing the momentum of escaping gas, or perfectly symmetric outgassing that cancels itself out. Some researchers propose that 3I Atlas might have an unusually dense core, perhaps composed of heavier elements like iron or nickel, which could act as a stabilizing force. Others point to its symmetrical shape, hypothesizing that the gas and dust escape uniformly in all directions, negating any net acceleration. However, both theories strain credulity. No known comet or asteroid behaves this way. The second interpretation ventures into speculative territory. What if something is actively stabilizing the object, minimizing detectable drift? This idea, while controversial, has gained traction among a small but vocal group of scientists. They cite the object's unusual origin. 3I Atlas is not native to our solar system. Detected in 2017, it was identified as the second interstellar object ever observed, hurtling through our cosmic neighborhood at over 30 kilometers per second. Its alien nature adds an extra layer of mystery. Could it be a natural object with properties unknown to our solar system? Or, in the most audacious of theories, could it be something more, an artifact of an extraterrestrial civilization? The stakes are astronomical. 3I Atlas won't linger forever, as it retreats toward Interstellar. Space. It carries its secrets with it. Every passing day brings it closer to the edge of our detection limits. Already it's over 200 million kilometers from Earth, its faint signal growing weaker with each observation. By 2023, it will fade from the view of even our most powerful telescopes, leaving behind only questions and the data we've managed to collect. What's known, 3I Atlas is venting gas and dust. Confirmed by multiple telescopes, its trajectory remains unchanged despite this activity, and its interstellar origin has been verified. What's unknown? Why isn't it accelerating? Are natural processes at work, or is there an artificial stabilization mechanism? And perhaps most pressing, will we solve this puzzle before it vanishes into the cosmic void? The countdown to perihelion has begun. As 3I Atlas makes its closest approach to the Sun, the outgassing will intensify, offering astronomers a final opportunity to study its behavior in detail. Teams around the world are working tirelessly, coordinating observations across dozens of telescopes. But time is unforgiving. Each night brings the object closer to the edge of our understanding, a fleeting visitor that may never return. The universe has thrown us a cosmic riddle, and the clock is ticking. Part 2. Discovery and Early Mysteries. How did 3I Atlas slip into our solar system undetected? The story of 3I Atlas begins with a faint point of light drifting against the stellar backdrop. On July 1, 2025, the Atlas telescope in Chile captured something unusual, an object moving too fast to be a typical asteroid. At 25 kilometers per second, it was clearly not bound by the Sun's gravity. Within days, astronomers confirmed the impossible, a hyperbolic trajectory, the signature of an interstellar visitor. The last time this had occurred was with Oumuamua in 2017 and Borisov in 2019. But 3I Atlas was different. Its trajectory was steeper, its approach more dramatic, and its behavior more enigmatic. The mysteries were just beginning. The object appeared to emerge from the constellation Sagittarius, a crowded stellar neighborhood that made early measurements a game of precision. Sagittarius, home to the galactic core, is a region teeming with stars, gas clouds, and cosmic noise. Astronomers had to sift through this celestial chaos to pinpoint 3I Atlas's exact path. As more data arrived, the picture became clearer and stranger. 3I Atlas was brightening rapidly, developing a coma and tail as it approached the sun. By mid-July, its coma, the glowing envelope of gas and dust surrounding the nucleus, was visible even in smaller observatories. Yet something didn't add up. The brightening was dramatic, but was it purely due to outgassing, or was there more to the story? Hubble's iconic image from July 21st revealed a distinct sun-facing plume, confirming active outgassing. The plume stretched over 100,000 kilometers, glowing ethereally against the void of space. But faint, ghostly features hinted at something more, an anti-tail pointing toward the sun, a phenomenon seen in some solar system comets but rare enough to raise questions. Anti-tails form when dust particles are pushed back by solar radiation pressure, creating a false tail that seems to defy physics. For 3I Atlas, this anti-tail was unusually pronounced, suggesting a composition rich in fine dust or reflective materials. By August 27th, Gemini South Observatory captured the transition to a more conventional tail, leaving astronomers with a growing puzzle. If 3I Atlas is so active, why isn't it accelerating? Observation. The object's tail exhibited a distinct curvature indicating the presence of dust grains of varying sizes. Larger grains, less affected by solar radiation, trailed behind, while smaller particles were pushed outward, creating a delicate, sweeping arc. This curvature was more pronounced than in most solar system comets, hinting at a unique composition or internal structure. Speculation. Some researchers proposed that 3I Atlas might be a fragment of a larger interstellar body, shattered by an unknown cataclysm in its home system. This could explain its unusual brightening and the faint anti-tail, a remnant of its violent past. Others suggested it might be a manufactured object, its reflective properties and strange trajectory hinting at artificial origins. As the object approached perihelion, its closest point to the sun, the answers may lie in the evolving tail structures. The intense solar heat would reveal the object's true nature, burning away its outer layers and exposing the mysteries within. Astronomers worldwide turned their telescopes toward the approaching visitor, eager to unravel its secrets. Meanwhile, the public watched with bated breath, captivated by the possibility of another interstellar enigma. The stage was set for a celestial drama unlike any other. Interpretation. The faint anti-tail could be a clue to the objects. Composition. If it contains highly reflective materials such as metallic compounds or icy grains, this could explain the unusual brightening. Alternatively, the anti-tail might be a result of a recent outburst or fragmentation event, where a sudden release of material created the ghostly feature. As September approached, 3I Atlas continued to defy expectations. Its brightness fluctuated unpredictably, with sudden surges followed by inexplicable dimming. Some astronomers theorized that the object was tumbling, its irregular shape causing wild variations in reflectivity. Others suggested that the fluctuations were evidence of ongoing fragmentation, with pieces breaking off and drifting into space. Each new observation added more questions than answers, deepening the mystery of this interstellar intruder. The world watched in awe as 3I Atlas drew nearer, its tail stretching across the sky. Like a cosmic banner, amateur astronomers shared images of the object, its faint glow visible even in modest backyard telescopes. Social media buzzed with speculation, from scientific theories to wilder ideas about alien civilizations and interstellar messages. Meanwhile, professional observatories worked tirelessly to capture every detail of the object's behavior, hoping to uncover the truth before it vanished into the depths of space once more. The countdown to perihelion had begun, and with it, the race to solve the enigma of Three-Eye Atlas. Part 3. What NGA means in practice. Could physics as we know it be flawed? This question troubles astronomers as they grapple with the mysteries of Comet Three-Eye Atlas. To understand this puzzle, we must examine non-gravitational acceleration, NGA, a phenomenon observed in comets for decades. Since its detection in the 1950s, NGA has been vital in refining comet motion models, but remains poorly understood. Imagine riding a skateboard while holding a leaking water bottle, the escaping. Water propels you backward. This rocket effect also governs comets. Measuring it on distant objects requires extraordinary precision. Tools like the Hubble Space Telescope and Pan-STARRS detect shifts as small as a few milliarc seconds, enabling the tracking of over 4,000 comets, each with unique NGA challenges. Through high-precision astrometry, scientists track these objects looking for deviations from gravitational motion. They account for every known force, including the sun's pull and planetary perturbations. After modelling these influences, they search for residuals, unexplained discrepancies indicating NGA. This process involves meticulous calculations, with errors as small as 0.01 arc-seconds potentially skewing results. Most comets exhibit predictable NGA. As they approach the sun, their icy surfaces release gas and dust jets, altering their trajectories. Halley's Comet, for example, shows clear NGA during its approach, with outgassing jets shifting its path by up to 0.1 arc-seconds daily. Comet 67P Churyumov-Gerasimenko has shown deviations as large as 10 kilometers from its expected position over a few months. Three-Eye Atlas, however, defies this logic. Despite evident outgassing and a 100,000-kilometer tail, the expected NGA remains undetected. This isn't mere curiosity, it challenges our understanding of comet physics and momentum. Conservation. If unresolved, it could force astronomers to re-evaluate fundamental assumptions underlying comet dynamics. Observations confirm Three-Eye Atlas is actively outgassing, with a coma and tail containing water vapor and other volatiles. Yet the absence of detectable NGA suggests either insufficient outgassing to produce a measurable effect or an unseen force counteracting the acceleration. One study estimated the comet's outgassing rate at 100 kilograms per second, well within the range expected to produce noticeable NGA. One hypothesis is that Three-Eye Atlas is unusually massive, with a dense core resisting acceleration more than typical comets. Alternatively, its outgassing jets may be symmetrically distributed, cancelling out net acceleration. Another possibility is an unseen companion perturbing its path and masking NGA effects. Some researchers proposed that Three-Eye Atlas may have fragmented in the past, leaving behind a denser, less active core. Astronomers are employing cutting-edge techniques to solve this puzzle. The James Webb Space Telescope, with its infrared sensitivity, could reveal hidden factors in Three-Eye Atlas's composition. Ground-based observatories are conducting long-term monitoring to track its trajectory with unprecedented precision. Three-Eye Atlas's behavior has sparked debates among scientists. Some argue it represents a new class of comets, defying traditional classification. Others suggest it may be transitioning from a comet to an asteroid-like body. Its erratic outgassing and lack of NGA have led some to propose it may be a dying comet, nearing the end of its active lifespan. Regardless of the explanation, Three-Eye Atlas reminds us that our understanding of the universe is incomplete. Could it unlock new physics, reshaping our understanding of celestial mechanics and cosmic forces? Part 4. Nickel in the coma. What does the chemistry of 3I Atlas tell us? The Very Large Telescope in Chile's Atacama Desert has spent decades dissecting starlight to reveal the chemical secrets of distant worlds. Perched atop Cerro Paranal, its 4 massive mirrors, each measuring 8.2 meters in diameter, collect faint light from the cosmos, channeling it into instruments that unravel the spectral fingerprints of stars, galaxies, and comets. When it turned toward 3I Atlas, it captured something genuinely puzzling, a chemical signature that challenges our understanding of comet behavior. The observatory's high-resolution spectrographs, capable of detecting shifts as subtle as a few centimeters per second, identified an unexpected elemental imbalance within the comet's coma, the glowing envelope of gas and dust that surrounds its icy nucleus. The spectrum revealed clear nickel emission lines, but iron, a common companion, in comet chemistry was conspicuously absent. This unusual chemical profile demands explanation. Nickel and iron are typically forged together in stellar furnaces, where temperatures exceeding 10 million degrees Celsius fuse lighter elements into heavier ones. These metals are then incorporated into planetary materials as partners, forming the basis of asteroids, comets, and even the rocky planets themselves. Their separation in 3I Atlas suggests an exotic formation history or an unknown process at work. The comet's nickel-to-iron ratio is estimated to be at least 10 times higher than that of typical comets, a discrepancy that has sparked intense debate among astronomers and planetary scientists. Several natural explanations are under investigation. Space weathering, a process driven by solar wind particles and micrometeoroid impacts, could preferentially liberate nickel-bearing compounds from the nucleus. Meanwhile, solar ultraviolet radiation, which bathes the comet in high-energy photons, breaks down these compounds, freeing nickel atoms to glow brightly in the spectrum. However, this hypothesis struggles to account for the complete absence of iron, as similar processes should, in theory, release both metals in comparable amounts. Another possibility is that 3I Atlas formed in a region of the early solar system where nickel was unusually abundant, perhaps near a supernova remnant that seeded the surrounding gas cloud with nickel-rich dust. Some commentators, however, have ventured into more speculative territory, suggesting that the nickel signature might mirror the erosion of nickel-based superalloys used in high-temperature engineering applications. These alloys, which contain high concentrations of nickel, chromium, and cobalt, are prized for their strength and resistance to corrosion under extreme conditions. They are commonly used in jet engines, gas turbines, and nuclear reactors, environments where materials must withstand temperatures exceeding 1000 degrees Celsius. If such an alloy were exposed to the vacuum of space, its surface would slowly degrade, releasing nickel atoms into the surrounding environment. This interpretation transforms a chemistry puzzle into a technology signature, though it remains firmly in the realm of hypothesis. Observation. The nickel emission lines in 3I Atlas are unusually strong, suggesting a high concentration of the metal in the comet's coma. Interpretation. The absence of iron is difficult to reconcile with traditional models of comet formation, which predict similar abundances of both metals. Speculation. If the nickel signature is indeed the result of erosion from a nickel-based superalloy, it would imply the presence of an engineered object embedded within the comet or its nucleus. However, such an object would need to have survived the comet's long journey through interstellar space, a scenario that raises more questions than it answers. What's known? 3I Atlas has an unusual nickel-to-iron ratio, with nickel emission lines at least 10 times stronger than those typically observed in comets. What's unknown? Is this a natural chemical anomaly? A. Consequence of an unusual formation environment, or a technological signature? The answer may lie in the object's unusual composition. To unravel this mystery, astronomers will need to gather more data, possibly through additional spectroscopic observations or even a dedicated mission to study 3I Atlas up close. Such efforts could reveal whether the comet's nickel-rich chemistry is a quirk of nature or a hint of something far more extraordinary. Part 5. The Mass Argument. Could 3I Atlas be too massive to move? Sometimes the simplest physics provides the most profound insights. The rocket equation, which governs spacecraft propulsion, also applies to comets. Thrust equals mass flow rate times exhaust velocity. If you can measure the thrust and estimate the gas flow, you can infer the mass. And when researchers applied this logic to 3I Atlas, they arrived at a stunning conclusion. The implications are profound, are massive. Object hurtling through space, defying easy classification and challenging our understanding of celestial mechanics. The James Webb Space Telescope's NIR spec instrument observed 3I Atlas on August 6, 2025. Providing unprecedented measurements of its carbon dioxide plume. The team derived gas production rates and outflow velocities with precision impossible from ground-based observations alone. The data revealed a plume extending over 10,000 kilometers. With gas ejected at velocities exceeding 500 meters per second, combined with the upper limits on observed non-gravitational acceleration, these numbers paint a picture of an object that might be far more massive than its brightness suggests. The plume's structure, captured in infrared wavelengths, showed intricate detail, hinting at complex processes beneath the surface. One interpretation, advanced by researchers including Harvard's Abraham Loeb, combines the JWST outgassing data with the conspicuous absence of robust NGA detection to infer a nucleus mass of at least 3.3 x 10 to 10 metric tons, roughly equivalent to a small mountain. If this mass estimate proves accurate, it would explain the missing non-gravitational acceleration through pure Newtonian physics. A sufficiently massive nucleus could absorb the momentum of escaping gas without measurable deflection, like trying to push a cargo. Ship with a garden hose. The sheer scale of such an object raises questions about its origin and composition, as well as its potential impact on our understanding of the solar system's formation. But mass estimates for distant objects remain frustratingly uncertain. Hubble imaging efforts continue working to constrain the nucleus size and albedo, the reflectivity that determines how much light it absorbs versus reflects. Coma brightness can mislead. Observers about the true size of the underlying solid nucleus, especially when that nucleus remains unresolved even by our most powerful telescopes. For example, comet 67P Churyumov-Gerasimenko, visited by the Rosetta mission, had a nucleus just 4 kilometers wide, yet its coma stretched millions of kilometers into space. The challenge with 3I Atlas is magnified by its distance, over 10 times farther from Earth than 67P was during Rosetta's encounter. Observation. The coma of 3I Atlas appears unusually bright for its distance, suggesting either a highly active surface or a larger nucleus than initially assumed. Interpretation. If the nucleus is indeed massive, it could imply an object with a density far greater than typical comets, which are often compared to dirty snowballs with low bulk density. Speculation. Could such a dense object be natural, or does its composition hint at something more? exotic. To refine these estimates, researchers are turning to additional tools. Radar observations, though limited by distance, could provide constraints on the object's shape and rotation. Meanwhile, spectroscopic analysis of the coma's composition could reveal clues about the nucleus itself. For instance, the presence of certain isotopes or unusual chemical signatures might suggest a formation environment unlike anything in our solar system. The European Southern Observatory's extremely large telescope, set to begin operations in the late 2020s, could play a pivotal role in these studies, offering resolution unmatched by any existing ground-based facility. The mass argument, however, is not without controversy. Critics point out that the lack of detectable non-gravitational acceleration could be explained by factors other than mass, such as an unusually slow outgassing rate or a coma dominated by fine dust rather than gas. Others argue that the current data is too limited to rule out more mundane explanations. For example, a 2026 study proposed that 3I Atlas might be a fragment of a larger, disintegrating comet, its unusual properties the result of recent fragmentation rather than intrinsic mass. Despite these debates, the possibility of a massive 3I Atlas has sparked renewed interest in the broader question of how such objects form and evolve. If confirmed, it would join a small but growing list of enigmatic bodies that defy easy categorization. These include Oumuamua, the first interstellar object ever observed, and Borisov, a comet with an unusually high velocity suggesting an origin outside the solar system. Each of these objects has forced astronomers to rethink their assumptions about the dynamics of the cosmos, and 3I Atlas may prove no different. What's known, 3I Atlas, may be unusually massive. What's unknown, is the mass natural or artificial? The answer may lie in the object's density and composition. As telescopes continue to gather data, the mystery of 3I Atlas deepens, drawing astronomers into a cosmic detective story with implications far beyond our solar system. Part 6. Lessons from Oumuamua. What can the first interstellar visitor teach us? On October 19, 2017, the Pan-STARRS telescope in Hawaii detected something extraordinary. Humanity's first confirmed interstellar visitor. Named Oumuamua, Hawaiian for scout or messenger, this object defied classification. It looked like a dead rock tumbling through space, following a hyperbolic trajectory that confirmed its interstellar origin. Yet, when astronomers began precision orbit determinations, something extraordinary emerged from the data. Oumuamua was accelerating. The object's trajectory was carefully reconstructed using data from observatories around the world, including the European Southern Observatory's Very Large Telescope in Chile and the Canada-France-Hawaii Telescope. The results were undeniable. Oumuamua was not behaving like any comet or asteroid ever observed. The magnitude of this non-gravitational acceleration, approximately 4.9 x 10⁶ ms2 at 1 astronomical unit from the Sun, was statistically significant to 30 standard deviations, meaning the probability of this being a measurement error was essentially zero. Yet no visible outgassing or dust emission could account for such a strong force. This created what astronomers diplomatically call an interesting problem. How do you accelerate a seemingly inert object without any visible mechanism for creating thrust? The mystery deepened as telescopes across the globe trained their lenses on Oumuamua, capturing its faint, rapidly fading light. By the time it was discovered, Oumuamua was already on its way out of the solar system, making observations increasingly difficult. Its strange behavior left astronomers with more questions than answers. The controversy that followed spawned dozens of research papers exploring increasingly exotic possibilities. Could solar radiation pressure alone account for the acceleration if the object had an unusually high area-to-mass ratio? Might it be venting transparent gas that escaped detection by conventional spectroscopy? Did its unusual elongated shape somehow amplify thermal re-radiation effects? Each proposed solution required assumptions that stretched conventional comet physics to its breaking point. One hypothesis suggested that Oumuamua was a hydrogen iceberg, a fragment of a molecular cloud ejected into interstellar space. However, such an object would have sublimated completely before reaching our solar system, making this explanation unlikely. Another idea posited that Oumuamua was a dust bunny, a loose aggregation of dust grains held together by weak electrostatic forces. But this too failed to explain the observed acceleration. Perhaps most intriguingly, some researchers suggested that Oumuamua might not be a natural object at all. The combination of its unusual trajectory, extreme aspect ratio, and unexplained acceleration led to speculation about artificial origins, a possibility that captured public imagination while dividing the scientific community. Harvard astrophysicist Avi Loeb argued that Oumuamua's behavior was consistent with a light sail, a thin, lightweight structure designed to harness solar radiation for propulsion. Loeb's hypothesis, while controversial, highlighted the need for caution when dismissing extraordinary explanations. If Oumuamua were artificial, it would imply that humanity is not alone in the universe, a prospect both thrilling and unsettling. However, most astronomers remained skeptical, pointing out that natural explanations, though elusive, were still more likely. Observation. Oumuamua's light curve suggested it was highly elongated, with a length at least 5 to 10 times its width. This shape was unlike anything seen in the solar system, further fueling debates about its origin. Its tumbling motion, which caused its brightness to vary dramatically over short periods, added another layer of complexity to the puzzle. Some researchers proposed that Oumuamua's shape was the result of a violent collision in its distant past, perhaps in a planetary system far from our own. Others suggested that its elongated form was a natural outcome of erosion or sublimation over millions of years of interstellar travel. Interpretation: the lack of detectable outgassing or dust emission from Oumuamua challenged the idea that it was a typical comet. Comets, which are primarily composed of ice, normally exhibit visible comae, clouds of gas and dust, when heated by the sun. Oumuamua showed no such activity despite passing within 0.25 astronomical units of the Sun, closer than Mercury's orbit. This led some astronomers to classify it as an asteroid, though its interstellar origin complicated this classification. Others argued that Oumuamua might be a dead comet, a comet that had exhausted its supply of volatile materials after countless orbits around its parent star, leaving behind only a rocky core. Speculation: if Oumuamua were indeed an artificial object, its creators would have possessed advanced technologies far beyond humanity's current capabilities. A light sail, for example, would require materials with exceptional strength-to-weight ratios and the ability to withstand the harsh conditions of interstellar space. The fact that Oumuamua survived its journey through the inner solar system without disintegrating suggests it was remarkably robust. Alternatively, if Oumuamua were a natural object, its unusual properties could offer insights into the formation and evolution of planetary systems beyond our own. By studying interstellar visitors like Oumuamua, astronomers hope to better understand the diversity of objects that populate the galaxy. What's known? Oumuamua exhibited unexplained acceleration. What's unknown? Was it natural or artificial? The lessons from Oumuamua may help us understand 3i Atlas, as astronomers continue to refine their models and search for similar objects. The legacy of Oumuamua will endure. Its brief visit to our solar system was a reminder that the universe is vast and full of surprises. Future missions, such as the upcoming Legacy Survey of Space and Time, LSST, at the Vera C. Rubin Observatory will scan the skies with unprecedented sensitivity, increasing the likelihood of detecting more interstellar visitors. Each new discovery will bring us closer to unraveling the mysteries of the cosmos and our place within it. Part 7. Lessons from 2i Borisov. What does a normal interstellar comet look like? On August 30th, 2019, Gennady Borisov, an amateur astronomer in Crimea, detected an unusual object in the constellation Lynx. Initial observations revealed it was moving at an odd speed and trajectory, and within weeks, calculations confirmed it as the second known interstellar visitor, named 2i Borisov. Unlike Oumuamua, which confused scientists with its shape and lack of cometary activity, Borisov behaved like a classic comet. Its discovery sparked a global effort, with astronomers training over a dozen world-class telescopes on the object, capturing its evolution in unprecedented detail. As Borisov approached the Sun, it brightened dramatically, displaying clear cometary activity. Water and other frozen volatiles began sublimating, creating a glowing coma over 100,000 kilometers wide and a tail stretching millions of kilometers. Spectroscopic analysis revealed familiar chemicals, water vapor, carbon monoxide, diatomic carbon, and cyanogen, all common in solar system comets. The comet's surface reflected a reddish hue, consistent with organic rich materials processed by cosmic radiation over millions of years. At its closest approach to the Sun, Borisov released up to 20 kilograms of dust per second, painting a vivid picture of a dynamic, active object. Borisov's trajectory confirmed it. Was not gravitationally bound to the Sun, moving at over 33 kilometers per second on a hyperbolic path. Its non-gravitational acceleration, caused by outgassing, matched theoretical predictions demonstrating comet physics on an interstellar scale. This behavior provided a baseline for understanding interstellar comets, showing they can follow the same natural laws as local ones. Borisov's path was traced back to the outer reaches of the galaxy, suggesting it had been wandering through interstellar space for millions, if not billions, of years. Observation. Borisov's normalcy was its defining feature. Its 0.7-kilometer nucleus and reddish color were unremarkable, resembling outer solar system comets. This similarity suggests that comet formation processes may be universal, occurring in protoplanetary disks around other stars under conditions like those in our early solar system. The detection of familiar gases like carbon monoxide, which requires extremely cold temperatures to form, hints that Borisov originated in a distant icy region of its home system, perhaps analogous to our Kuiper belt. Interpretation. Borisov's familiar behavior highlights the anomalies of Oumuamua and the debated interstellar comet 3i Atlas. While Borisov acted like a typical comet, Oumuamua's elongated shape, lack of coma or tail, and unexplained acceleration remain puzzling. 3i Atlas, discovered in 2020, showed unusual fragmentation, though its interstellar status is uncertain. Borisov's normalcy sharpens the contrast with these outliers, suggesting a greater diversity of interstellar objects than initially thought. The stark differences between these objects have led some astronomers to propose that interstellar visitors may come in distinct families, each shaped by different formation. Histories and journeys through the galaxy. Speculation. Borisov likely originated from a distant star system, ejected by gravitational interactions and drifting through interstellar space for millions of years. Its resilience implies that such comets might be common galactic wanderers. Future interstellar visitors could resemble Borisov or present entirely new characteristics, further expanding our understanding of the cosmos. Some researchers have even suggested that interstellar comets like Borisov could have played a role in seeding the early solar system with water and organic compounds, though this remains purely hypothetical. What's known, 2I Borisov behaved like a typical comet, confirming that interstellar objects follow familiar physical laws. Its composition and dynamics match solar system comets despite its extrasolar origins. The comet's journey through the inner solar system provided a rare opportunity to study an interstellar object up close, yielding valuable data about its structure, chemistry, and behavior. What's unknown? Why do Oumuamua and 3I Atlas differ so significantly? Are they unique, or do they represent a distinct class of interstellar objects? How common are Borisov-like comets, and what insights do they offer into the diversity of planetary systems across the galaxy? Astronomers continue to search for answers as they monitor the skies for the next interstellar visitor, hoping to uncover more clues about the universe beyond our solar system. Part 8. Other Comet Benchmarks. How do solar system comets compare to 3I Atlas? The European Space Agency's Rosetta mission spent 12 years escorting Comet 67P Churyumov-Gerasimenko, a modest object just 4 kilometers across. During this unprecedented close encounter, Rosetta's instruments captured over 100,000 images and recorded more than 30 types of organic molecules, including 4 never before detected in cometary material. The mission confirmed every aspect of theoretical predictions. Outgassing creates forces, forces alter orbits, and the magnitude of these changes depends predictably on gas production rates, exhaust velocities, and nucleus mass. Rosetta observed dramatic changes in the comet's surface, with cliffs collapsing and boulders moving as the icy body was heated by the sun. But size introduces complications. Consider Comet Hale-Bopp, one of the largest and most spectacular comets of recent decades, during its 1997 apparition. Hale-Bopp displayed a nucleus estimated at 60 kilometers in diameter, roughly 15 times larger than Churyumov-Gerasimenko. Its coma, the envelope of gas and dust surrounding the nucleus, extended over 1 million kilometers, larger than the Sun itself. Despite its massive size, Hale-Bopp still exhibited measurable non-gravitational acceleration as it approached the Sun, proving that even very large comets cannot entirely resist the rocket effect of their own emissions. Observations revealed that Hale-Bopp's outgassing produced jets with velocities exceeding 1 km/s, creating a thrust strong enough to perturb its orbit. The lessons from Hale-Bopp resonate directly with the 3I Atlas mystery. Mass provides inertia that dampens acceleration, but it doesn't eliminate the effect entirely unless the object reaches truly extraordinary scales. Comet Halley, for instance, with a nucleus of about 15 km, experiences non-gravitational forces that alter its orbit by as much as 160 km per day during its closest approach to the Sun. If 3I Atlas is indeed as massive as some estimates suggest, it should still show some measurable response to asymmetric outgassing if the jets are sufficiently powerful and directionally biased. The absence of such behavior in 3I Atlas raises questions about the nature of its composition or the mechanics of its outgassing. Comet 103P Hartley 2, visited by NASA's Epoxy mission in 2010, provides another critical comparison. This small comet, just 1.6 kilometers in diameter, exhibited jets of carbon dioxide that propelled it with enough force to visibly alter its rotation. The mission uncovered evidence of an icy, porous structure, with CO2 jets acting like thrusters, demonstrating how even small comets can undergo significant dynamic changes. The epoxy data highlighted the importance of outgassing patterns, showing that the orientation and distribution of jets can dramatically influence a comet's behavior. Observation: the diversity of comet behavior, from small bodies like Hartley 2 to giants like Hale-Bopp, underscores the universality of outgassing as a driving force in cometary dynamics. Interpretation 3I Atlas, if it conforms to known cometary processes, should exhibit some degree of non-gravitational acceleration, proportional to its size and outgassing activity. The absence of such effects could indicate either an unusual composition or a lack of significant outgassing. The answer may lie in the balance of forces at play. The delicate interplay between mass, outgassing, and external influences like solar radiation pressure shapes the behavior of every comet. For 3I Atlas, the lack of observed non-gravitational forces could suggest a composition so dense or inert that it resists the typical effects of outgassing. Alternatively, it could imply that the comet's activity is far lower than expected, raising questions about its origin and evolution. Speculation: if 3I Atlas is indeed of interstellar origin, its composition and behavior may reflect conditions far removed from our solar system. Its apparent stability could be a clue to its formation in an environment where outgassing plays a minimal role. Or it could hint at a structure fundamentally different from known comets. Future observations will be critical in untangling these mysteries, as the enigmatic object continues to defy easy classification. What's known: large comets can still exhibit non-gravitational acceleration. What's unknown: why doesn't 3I Atlas? As the scientific community continues to study 3I Atlas, the lessons from comets like Churyumov, Gerasimenko, Hale-Bopp, and Hartley 2 will guide the search for answers. Each of these comets has revealed new facets of cometary behavior, from the microscopic scale of molecular interactions to the macroscopic scale of orbital dynamics. Together, they provide a framework for understanding the forces that shape these icy wanderers, and for unraveling the secrets of 3I Atlas, a visitor from the cosmic depths. Part 9. The Artificial Control Hypothesis. Could 3I Atlas be stabilized by technology? In the careful language of peer-reviewed science, extraordinary hypotheses receive extraordinary scrutiny. The artificial control hypothesis for 3I Atlas falls into this rarefied category, speculative enough to raise eyebrows, yet grounded in sufficient anomalous observations that dismissing it entirely might constitute intellectual negligence. Since its discovery in 2017, 3I Atlas has defied conventional explanations, its trajectory and behavior sparking debates that have divided the astronomical community. The object's slight but measurable deviations from a purely gravitational trajectory have been attributed to natural outgassing, but the precision of these deviations has led some researchers to propose a more deliberate cause. The core premise rests on a simple engineering question. If you wanted to send a probe through interstellar space, While minimizing detectable signatures of artificial propulsion, how might you design such a system? The answer involves active stabilization using small thrusters or reaction control systems to counteract the random forces that would otherwise create detectable trajectory changes. Cold gas microthrusters could provide precise thrust in opposition to natural outgassing. Symmetric reaction control systems might balance asymmetric gas jets. Momentum wheels, coupled with low thrust venting, could maintain attitude while eliminating net acceleration. These systems would need to operate with extreme precision, correcting for forces as subtle as the radiation pressure from distant stars or the faint gravitational tugs of nearby celestial bodies. These aren't fantasy technologies. Human spacecraft have employed similar systems for decades. The International Space Station uses reaction control thrusters too. Counteract atmospheric drag, ensuring it remains in a stable orbit despite the constant tug of Earth's atmosphere. Deep space probes, such as NASA's Voyager and New Horizons missions, carry attitude control systems to maintain pointing accuracy despite solar radiation pressure and thermal effects. These systems are so finely tuned that they can compensate for forces as faint as the pressure exerted by sunlight, which, though minuscule, can accumulate over vast distances and affect trajectories. The engineering principles exist. The question becomes one of scale, sophistication, and motivation. Observation. 3I Atlas exhibits a slight acceleration that cannot be fully explained by gravitational forces alone. This acceleration is on the order of 0.0001 meters per second squared, a value so small it requires highly sensitive measurements to detect. For comparison, the acceleration due to Earth's gravity is approximately 9.8 meters per second squared, nearly 1,000,000 times greater. Yet, over interstellar distances, even this tiny acceleration could have profound effects on the object's trajectory. Interpretation. One explanation for this acceleration is natural outgassing, where sublimating ices on the object's surface create a weak thrust. However, the observed acceleration appears unusually consistent, lacking the random variations one might expect from natural processes. This consistency has led some researchers to propose that the acceleration could be the result of deliberate stabilization rather than chance. If true, this would imply the presence of an artificial control system capable of counteracting natural forces with precise, calculated adjustments. Speculation. If 3I Atlas is indeed stabilized by technology, the implications are staggering. Such a system would require a power source, likely a long-lived isotope or advanced energy storage mechanism. It would also need a guidance system capable of navigating interstellar space, possibly using celestial landmarks or distant stars as reference points. The craft itself would likely be designed to minimize detectability, using materials and shapes that scatter or absorb electromagnetic radiation to avoid reflecting starlight in ways that might reveal its artificial nature. What's known? The technology for artificial stabilization exists. Human spacecraft routinely use reaction control systems and microthrusters to maintain precise trajectories and orientations. These systems are well understood and have been deployed in missions ranging from Earth orbit to the outer reaches of the solar system. The principles of stabilization and propulsion are not theoretical. They are proven, functional, and scalable. What's unknown? Is it being used on 3I Atlas? The object's trajectory and behavior remain subjects of intense study, with researchers carefully monitoring its movements for any signs of deliberate control. As it approaches perihelion, its closest point to the Sun, the increased solar radiation and thermal effects could provide new insights into its nature. If the object's stabilization is artificial, these forces might reveal subtle corrections or adjustments that natural processes alone cannot explain. The answer may lie in the object's behavior as it approaches perihelion. As 3I Atlas draws nearer to the Sun, its surface will heat up, potentially triggering increased outgassing and creating new forces that any stabilization system would need to counteract. This period of heightened activity could expose the limitations, or the ingenuity, of whatever mechanism is guiding the object. Astronomers around the world are watching, their telescopes trained on the enigmatic visitor, waiting for the slightest hint of what lies beneath its silent, tumbling exterior. Part 10. Spectral Curiosities and Stability. What does the James Webb Space Telescope reveal? The James Webb Space Telescope's NIR-SPEC instrument doesn't just collect light, it dissects it with surgical precision, revealing the molecular fingerprints that tell stories of cosmic chemistry spanning billions of years. When this extraordinary machine focused on 3I Atlas during its August 6, 2025, observation run, the resulting spectrum painted a portrait of an object unlike any comet previously. Studied in detail, the data, transmitted back to Earth over a period of 7 hours, was immediately flagged by researchers at the Space Telescope Science Institute for its unprecedented chemical signatures. The most striking feature dominates the near-infrared wavelengths where carbon dioxide molecules absorb and re-emit photons with characteristic signatures. 3I Atlas exhibits one of the highest CO2 to H2O ratios ever measured in any comet, solar system or otherwise. The ratio clocks in at approximately 3.2 to 1, far exceeding the typical ratios of 0.3 to 1 found in most solar system comets. While most comets show water as their dominant volatile, this interstellar visitor appears powered primarily by carbon dioxide sublimation, with water vapor and carbon monoxide playing distinctly secondary roles in its activity patterns. This translates to a coma, the glowing, tenuous atmosphere surrounding the comet that is rich in CO2, giving it a faint, almost ethereal greenish hue when viewed through certain filters. This chemical dominance suggests formation scenarios that challenge our understanding of typical comet compositions. Most objects in our solar system formed in regions where water ice condensed readily, creating the characteristic ice-rock mixtures we observe in periodic comets. But 3I Atlas appears to have originated in an environment where carbon dioxide dominated the volatile inventory, perhaps near a CO2 ice line around a different type of star, or in a protoplanetary disk with unusual chemical gradients. Its spectrum also hints at the presence of complex organic molecules, including traces of methanol and formaldehyde, which are often precursors to life-supporting chemistry. Initial models of 3I Atlas's trajectory indicate it has been wandering the interstellar void for at least 1.3 million years, its surface battered by cosmic rays and UV radiation from distant stars. Despite this, its unusual chemical composition remains intact, suggesting it may have been shielded by an outer layer of more stable materials, or that its volatile inventory is replenished by some internal process. The comet's nucleus, estimated to be roughly 1.2 kilometers in diameter, appears unusually dense for its size, with a bulk density of about 0.8 grams per cubic centimeter compared to the 0.5 grams per cubic centimeter typical of solar system comets. This density could imply a higher proportion of rocky material or a more compacted structure, further hinting at an origin unlike anything in our own solar system. Observation. The comet's tail, stretching over 1.5 million kilometers, shows a distinct stratification of dust and gas, with heavier particles trailing behind the lighter, more. Volatile compounds. This stratification is particularly pronounced in images captured by the Hubble Space Telescope during its coordinated observation campaign with James Webb. The tail structure suggests that 3I Atlas has been shedding material at a steady rate for at least the past 6 months, with no significant outbursts or disruptions in its activity. Speculation. Could this stability be a sign of artificial control? Some researchers have proposed that the comet's unusual composition and steady behavior could be indicative of an engineered object designed to maintain its structure and chemical balance over vast interstellar distances. While this hypothesis remains highly speculative, it has sparked renewed interest in the search for technosignatures, evidence of advanced technology, in objects beyond our solar system. The answer may lie in the balance of forces at play. As 3I Atlas continues its journey through the inner solar system, astronomers are racing to gather as much data as possible before it fades from view. Its closest approach to Earth, scheduled for December 12, 2025, will bring it within 0.28 astronomical units, offering a rare opportunity to study its surface and composition in unprecedented detail. Ground-based observatories, including the Atacama Large Millimeter Sub-Millimeter Array, ALMA, in Chile, are already preparing to complement the space-based observations, probing the comet's molecular inventory with even greater sensitivity. Meanwhile, the Breakthrough Listen project, dedicated to the search for extraterrestrial intelligence, has begun monitoring 3I Atlas for any unusual radio emissions. Though no signals have been detected so far, the search will continue as the comet draws closer, its mysteries slowly unraveling under the scrutiny of human curiosity. The coming months will reveal whether 3I Atlas is a natural interstellar wanderer or something far more extraordinary, a beacon from the cosmos, carrying a message we have yet to decipher. What's known, 3I Atlas has an unusual chemical composition, a stable trajectory, and a highly stratified tail indicating steady outgassing. What's unknown, is this natural or artificial? And if artificial, what is its purpose? Part 11. Why this matters to SETI. For over 70 years, SETI has sought extraterrestrial signals, from Project Ozma in 1960 to today's Breakthrough Listen, which has scrutinized over 1,300 nearby stars and 100 nearby galaxies for technosignatures. This search has focused on detecting intentional electromagnetic transmissions, but 3I Atlas challenges this approach, suggesting we broaden our search to include accidental discoveries and physical artifacts, if interstellar objects like. 3IA Atlas are even occasionally artificial. They represent a paradigm shift for SETI, offering tangible evidence of extraterrestrial intelligence that doesn't require decoding radio waves or light pulses. Interstellar objects carry information about their origins and histories embedded in their composition, structure, and trajectories. Data that cannot be obscured or degraded over cosmic distances. These objects traverse the void for millions of years, bearing the fingerprints of their creators or environments. The Milky Way alone hosts over 100 billion stars, with recent studies suggesting as many as 6 billion Earth-like planets in habitable zones. Even if technological civilizations are rare, occurring in just 0.1% of these systems, that still leaves 6 million potential sources of interstellar artifacts. If even a fraction of these civilizations produce objects that outlive their creators. Millions of such artifacts could be drifting through the galaxy. Some may eventually find their way into our solar system, waiting to be detected and studied. In just 8 years, humanity has detected 3 confirmed interstellar visitors: Oumuamua in 2017, Borisov in 2019, and now 3I Atlas in 2028. 2 of these objects have already defied conventional explanations. Oumuamua's extreme elongation and unexpected acceleration have led some researchers to propose it could be an artificial light sail or advanced technology fragment. Borisov, though initially classified as a comet, exhibited a trajectory subtly altered by non-gravitational forces, sparking debates about its true nature. Now, 3I Atlas presents its own enigmas, with an unstable orbit suggesting recent ejection from another star system, and spectral anomalies hinting at a unique composition. This frequency of anomalies, 3 objects in, less than a decade each presenting unique challenges, suggests that unusual behavior among interstellar objects may be common enough to warrant systematic study. Future missions could intercept these travelers, deploying swarms of probes equipped with advanced spectroscopy instruments to detect artificial signatures. These probes could search for unnatural isotopic ratios, rare earth elements, or complex molecules that would not survive interstellar. Journeys without technological intervention. They could also map the object's surface in unprecedented detail, identifying geometric patterns or structures that defy natural explanations. Even subtle deviations from expected shapes or material distributions could provide compelling evidence of extraterrestrial technology. Confirming even one artificial object would revolutionize our understanding of the universe, proving beyond doubt that we are not alone in opening profound questions about the nature and history of other civilizations. Such a discovery would not only transform science, but also unite humanity in ways previously unimaginable. The confirmation of extraterrestrial intelligence, even in the form of an inert artifact, would inspire global cooperation in scientific research and space exploration on an unprecedented scale. Nations might set aside their differences to pool resources and expertise, collaborating on missions to study these objects up close, or even reverse engineer their technologies. It would challenge us to confront our limitations and prepare for the possibility of first contact with humility and wisdom. The detection of interstellar objects is accelerating, with Oumuamua in 2017, Borisov in 2019, and 3I Atlas in 2028. And this is likely just the beginning. As our observational capabilities improve, so does the likelihood of encountering something extraordinary. This growing frequency of detections is not mere chance, but a result of advancing technology and increased awareness. Next-generation telescopes like the Vera C. Rubin Observatory, set to begin operations in 2024, will allow us to scan the sky with unprecedented sensitivity, potentially detecting dozens of interstellar objects per year. If even a small percentage of these objects are artificial, it's only a matter of time before we find one. 3I Atlas may be just the beginning. In the coming decades, we could identify countless interstellar objects, transforming SETI into a robust, multidisciplinary field with dedicated observatories, intercept missions, and perhaps even space-based laboratories designed to study these visitors in situ. This future would compel us to engage with extraterrestrial technologies, grappling with their ethical, philosophical, and practical implications. It would also force us to reckon with our place in the cosmos, shifting our perspective from one of isolation to one of connection with a vast interstellar community. 3I Atlas is more than just another visitor. It's a harbinger of a future where humanity actively seeks out and learns from the physical evidence of other civilizations. It reminds us that the search for extraterrestrial intelligence is not limited to listening for distant signals, but also involves looking closely at the objects that pass through our cosmic neighborhood. In doing so, we may one day join these civilizations among the stars, not as passive observers, but as active participants in the grand conversation of the universe. Part 12. Observational Windows Ahead. What will perihelion reveal? The cosmic ballet proceeds according to precise mathematical choreography, and for 3i Atlas, the most important performance approaches its climax. October 30th, 2025 marks the object's perihelion passage, its closest approach to our Sun at approximately 1.4 astronomical units. This encounter represents our best and perhaps final opportunity to extract definitive answers about this enigmatic interstellar visitor before it fades back into the cosmic deep. At this distance, the Sun's intensity will be roughly 3 times greater than what 3i Atlas experienced during its discovery phase, subjecting the object to temperatures exceeding 400 Kelvin. This thermal stress could trigger cascading effects, offering astronomers a front-row seat to potential transformations on its surface or within its structure. Orbital geometry governs everything in observational astronomy, and the changing angles between Earth, 3i Atlas, and the Sun will dramatically alter our viewing perspective over the coming weeks. As the object swings around perihelion, different surface regions will experience peak solar heating, potentially triggering new outgassing patterns or revealing compositional variations across the nucleus. If artificial systems are indeed maintaining trajectory stability, increased thermal stress might finally overwhelm their capabilities and produce detectable acceleration signatures. Telescopes like the Vera Rubin Observatory will be perfectly positioned to capture these subtle shifts, with its 3200 megapixel camera capable of imaging the entire visible southern sky every few nights. The enhanced solar flux at perihelion distance will also amplify spectroscopic signals, making faint emission lines more readily detectable and enabling precision measurements of isotopic ratios that could distinguish between natural and artificial material sources. Elements present in trace quantities might finally exceed detection thresholds, potentially resolving the mysterious nickel without iron abundance pattern that has puzzled researchers since. For instance, the presence of certain rare isotopes like nickel-62, which is virtually absent in the solar system but more common in extragalactic environments, could provide strong evidence for the object's interstellar origins. Observation. Ground-based observatories will be joined by space-based assets like the James Webb Space Telescope, JWST, which with its infrared capabilities can probe the thermal properties of the object's surface. JWST's sensitivity to mid-infrared wavelengths will allow it to detect heat signatures that could indicate the presence of artificial materials or structures, as these would exhibit distinct thermal behaviors compared to natural cometry or asteroidal surfaces. Additionally, the Hubble Space Telescope will provide high-resolution imaging, potentially capturing changes in the object's morphology or orbit that could hint at internal activity or structural integrity issues. Interpretation. The data collected during perihelion will be invaluable for refining models of 3i Atlas's composition and history. For example, if the object exhibits significant outgassing, it could suggest the presence of volatile ices buried beneath its surface, which would point to a cometary origin. Conversely, if the object remains inert despite the intense solar heating, it might indicate a more rocky or metallic composition, consistent with an asteroidal classification. Any deviations from expected behavior could also fuel speculation about artificial origins, though such interpretations will require extraordinary evidence to overcome skepticism. Speculation. Some researchers have proposed that 3i Atlas could be a defunct or dormant technological artifact, perhaps a remnant of an extraterrestrial civilization. While this hypothesis remains highly speculative, the perihelion passage offers a unique opportunity to test it. If the object exhibits any signs of artificial construction, such as geometric shapes, unusual spectral signatures, or intentional maneuvers, it would revolutionize our understanding of the universe and our place within it. However, such discoveries would also raise profound ethical, philosophical, and scientific questions, requiring careful consideration and global cooperation to address. What's known? Perihelion is approaching. What's unknown? Will it reveal the object's secrets? The answer may lie in the data collected during this critical window. The coming months will see a coordinated effort across multiple observatories, with teams working around the clock to analyze incoming data. Every telescope, from the giant Mauna Kea observatories in Hawaii to the Atacama Large Millimeter Array, ALMA, in Chile, will contribute its unique capabilities to this unprecedented investigation. As the countdown to perihelion begins, the world watches, hoping that this fleeting cosmic encounter will unlock the mysteries of 3i Atlas and perhaps even redefine our understanding of the cosmos. Part 13. The Vera Rubin Era. How will future telescopes transform our understanding of interstellar visitors? The Legacy Survey of Space and Time, conducted by the Vera C. Rubin Observatory atop Cerro Pachon in Chile, will transform our understanding of the dynamic universe beginning in 2025. Every 3 nights, this revolutionary facility will image the entire southern sky to unprecedented depth, creating a time-lapse movie of cosmic evolution that spans a decade of continuous observations. Perched at an altitude of 2,700 meters, the observatory's 8.4-meter Simony Survey telescope will capture over 800 panoramic images each night, cataloguing billions of galaxies and solar system objects with breathtaking precision. For interstellar visitor research, this capability represents a quantum leap that will multiply discovery rates by orders of magnitude. Current interstellar object detection relies heavily on serendipity and the dedicated efforts of surveys like Atlas, Linear, and the Catalina Sky Survey. These programs have proven remarkably successful at finding unusual objects, but their sensitivity and sky coverage limits mean that we likely miss many faint, fast-moving visitors that pass through our solar system undetected. Rubin's combination of wide field coverage, deep limiting magnitudes reaching 24th magnitude, and rapid cadence will dramatically expand our ability to catch interstellar visitors during their brief transit through observable space. Its 3,200 megapixel camera, the largest digital camera ever constructed, will enable scientists to track objects as small as 100 meters in diameter, unveiling a hidden population of interstellar travelers that have eluded detection until now. The numbers illustrate the transformative potential. Current surveys detect perhaps 1 interstellar visitor every few years, providing a sample size barely adequate for statistical analysis of their properties and behavior patterns. Rubin projections suggest we might discover dozens of such objects annually once the survey reaches full operational capacity, creating datasets rich enough to distinguish between normal variations and genuinely anomalous characteristics. This influx of data will allow astronomers to refine models of interstellar object origins, trajectories, and compositions, shedding light on the processes that eject these wanderers from their home star systems. The observatory's advanced systems will also enable real-time processing of data, allowing for rapid follow-up observations of newly discovered objects. This capability will be crucial for characterizing interstellar visitors, as their transient nature often leaves astronomers with a narrow window of opportunity to study them before they disappear into the cosmic void. With Rubin's unprecedented observational power, scientists will be able to mobilize global networks of telescopes to scrutinize these objects in detail, revealing their secrets through spectroscopy, photometry, and high-resolution imaging. Observation. The Vera Rubin Observatory's ability to detect faint, fast-moving objects will revolutionize our understanding of interstellar visitors, providing insights into their origins, compositions, and dynamics. Speculation. The data collected by Rubin could reveal entirely new classes of interstellar objects, challenging our current theories of planetary system formation and evolution. What's known? The Vera Rubin Observatory will revolutionize interstellar visitor detection. What's unknown? What will it reveal? The answer may lie in the diversity of these objects. Imagine a future where interstellar visitors are not rare curiosities but routine discoveries, each one a messenger from distant stars. Rubin's unprecedented survey capabilities will not only increase the quantity of known interstellar objects, but also unveil their diversity. From icy comet-like bodies to rocky asteroidal fragments, these visitors may represent a wide range of formation histories and evolutionary pathways. By studying their compositions and trajectories, astronomers will gain insights into the conditions that shaped their birth and the forces that propelled them into interstellar space. The observatory's data will also inform our understanding of the interstellar medium itself, the tenuous gas and dust that fills the vast spaces between stars. As interstellar objects traverse this medium, they interact with it in ways that can alter their surfaces and compositions, leaving telltale signatures that Rubin's sensitive instruments will detect. These interactions could provide clues about the density, temperature, and chemical makeup of the interstellar medium, helping to refine models of galactic structure and evolution. In addition to its scientific impact, the Vera Rubin Observatory will inspire a new generation of astronomers and the public alike. The prospect of discovering dozens of interstellar visitors each year will captivate imaginations, fueling curiosity about our place in the cosmos. Public outreach programs will share the observatory's findings in real time, allowing people around the world to participate in the excitement of exploration. Schools, museums, and planetariums will use Rubin's data to create immersive educational experiences, fostering a deeper appreciation for the wonders of the universe. Interpretation. The Vera Rubin Observatory represents a paradigm shift in astronomy, one that will redefine our understanding of interstellar visitors and their role in the cosmic ecosystem. As the observatory begins its decade-long survey, it will not only uncover the mysteries of interstellar visitors, but also remind us of the vast, unexplored frontiers that lie beyond our solar system. Each new discovery will be a testament to the boundless potential of human ingenuity and the enduring quest to understand our place in the universe. The Vera Rubin era promises to be a golden age of astronomical discovery, one that will rewrite the textbooks and inspire future generations to reach for the stars. Part 14. Alien Artifact or cosmic oddball. What is 3-Eye Atlas? After extensive observation since its 2019 detection, the origins of 3-Eye Atlas remain elusive. Traversing millions of kilometers, the object's trajectory brought it within 37.9 million kilometers of the Sun, offering scientists a trove of data, but few definitive answers. Telescopes like Hubble and the Large Binocular Telescope in Arizona have tracked its journey, revealing both familiar and perplexing traits. Mainstream planetary. Scientists suggest 3-Eye Atlas is an interstellar comet, shaped by natural processes under exotic conditions. Its CO2-rich composition indicates formation near a carbon dioxide ice line in its birth system. Observations show classic cometary behavior, such as tail structures evolving in response to solar heating. As it neared the Sun, its coma expanded to over 100,000 kilometers, larger than Jupiter. Unusual features like anti-tail formations align with patterns seen in solar system comets under specific conditions. Observation. 3-Eye Atlas exhibits periodic brightness fluctuations likely from the rotation of an irregular nucleus. This behavior resembles comets like 67P Churyumov-Gerasimenko, though the amplitude is unusually high. Spectroscopic analysis revealed variations in surface composition, with reflective and darker regions suggesting a heterogeneous nucleus of ices and minerals. Accreted over billions of years. Interpretation. These fluctuations could result from its interstellar journey. Simulations suggest millions or billions of years of cosmic rays, interstellar gas, and gravitational forces shaped 3-Eye Atlas uniquely. Its elongated shape might be a product of prolonged weathering or deliberate design for interstellar travel stability. Some researchers argue that the object's combined anomalies defy natural explanation. Active stabilization systems could explain its lack of detectable non-gravitational acceleration despite asymmetric outgassing. Micro-thrusters or control systems might counteract natural thrust vectors, maintaining trajectory stability. For instance, the object's trajectory deviated by less than 0.01 degrees over 6 months, unprecedented in natural comets. Speculation. If 3-Eye Atlas is artificial, its purpose is unknown. It could be a defunct probe, an active reconnaissance device, or a fragment of a larger structure. The lack of detectable communication signals suggests advanced transmission methods, like quantum entanglement or neutrino-based communication, undetectable with current technology. Observation. 3-Eye Atlas followed a trajectory bringing it within 0.25 AU of the Sun at perihelion. This proximity subjected it to intense solar radiation and heat, with surface temperatures reaching an estimated 500 degrees Celsius. Interpretation. Perihelion allowed astronomers to study the object under extreme conditions. Its coma expanded dramatically, revealing a complex mixture of gases including carbon dioxide, carbon monoxide, and water vapor. These gases suggest a nucleus rich in ices, hinting at a diverse formation history. Infrared observations revealed localized temperature variations, possibly indicating insulating materials or internal heat sources. Speculation. During perihelion, subtle deviations from expected behavior were observed. The object's rotation rate changed slightly, possibly due to internal stress release or onboard system activation. Infrared observation showed localized temperature variations interpreted as heat dissipation from machinery. One hypothesis suggests a heat distribution system within the object to prevent thermal stress. During close solar approaches. Observation. As 3-Eye Atlas receded from the Sun, its coma and tail dissipated, but its brightness diminished more slowly than expected. This persistent luminosity could result from highly reflective surface materials or continued dust emission. Spectroscopic analysis detected traces of silicates and organic compounds, suggesting a complex surface chemistry. Interpretation. Post-perihelion behavior has led researchers to re-evaluate theories about the object's origin. If natural, its brightness might indicate unusual minerals or ices. If artificial, the brightness could be a deliberate feature to maximize visibility or facilitate communication. Some propose a reflective coating designed to withstand interstellar travel while minimizing heat absorption. Speculation. If 3i Atlas is artificial, its design suggests technology far beyond human capabilities. Its ability to withstand interstellar and solar conditions implies unknown materials and engineering principles. The lack of detectable communication raises questions about its purpose and data transmission methods. One theory suggests passive data collection, storing it for later transmission or retrieval by its creators. Observation. Astronomers are gathering data as 3i Atlas exits the solar system. Telescopes are capturing its diminishing light, revealing subtle changes in composition and structure. Recent observations using the James Webb Space Telescope detected faint emission lines associated with complex organic molecules, hinting at a rich chemical environment. Interpretation. This data may resolve the debate over 3i Atlas's origin. Analyzing outgassing materials and surface reflectivity could provide signatures of natural or artificial processes. Detection of complex organic molecules or unusual isotopic ratios might indicate an extraterrestrial technological origin. Speculation. Regardless of its classification, 3i Atlas has transformed our understanding of the cosmos. It underscores our solar system's place in a vast interstellar community. As technology advances, more interstellar visitors will likely be detected, offering new insights into the universe's diversity. Future missions like the Vera C. Rubin Observatory will dramatically increase our ability to spot these cosmic travelers. What's known, 3i Atlas is an interstellar object with unusual characteristics. What's unknown, is it natural or artificial? The answer may lie in the data collected during perihelion. Part 15. The Masked Broadcast Theory. Could 3i Atlas be hiding a message in its coma? This question persists as scientists study the comet's peculiar behavior. But what if we've been approaching this mystery from the wrong angle? Instead of asking why 3i Atlas shows activity without acceleration, consider this. What if a civilization deliberately designed such behavior? The masked broadcast theory, born from SETI research and signal processing concepts, suggests that 3i Atlas isn't concealing its artificial nature but broadcasting a message using universal chemistry. Picture an advanced civilization that has mastered interstellar communication. They might embed messages into the cosmos itself. The masked broadcast theory posits that 3i Atlas is an artifact engineered to emit a signal decodable by any species with sufficient technology. This theory recasts the comet's anomalies as intentional design rather than unexplained. Physics. The lack of non-gravitational acceleration, despite outgassing, becomes a carrier wave for a low bit-rate communication system, assuming young civilizations will study interstellar visitors. This theory has profound implications. Any species capable of spectroscopy could detect artificial modulation patterns in the coma's chemistry, creating a communication channel that requires no prior knowledge of alien languages or technology. The coma acts as a natural billboard, visible across vast distances, Subtle variations in chemical composition could encode complex messages, like Morse code written in the language of the stars. For instance, fluctuations in the ratio of carbon dioxide to water vapor could represent binary digits, while shifts in spectral line intensity might convey more intricate patterns. The elegance of this system lies in its universality. Spectral lines are physical. Constants, consistent across all civilizations. Hydrogen emits photons at 21 cm wavelength regardless of the observer. Carbon dioxide absorption features appear at the same frequencies whether detected by human or alien telescopes. A modulation scheme based on ratios such as CO2 to H2O abundance variations or isotopic signature changes would be universally readable. Imagine a civilization detecting a comet like 3I Atlas as they analyze its spectral signature. They notice anomalous patterns in common elements like oxygen, carbon, and hydrogen. These patterns follow a discernible sequence repeating at regular intervals. Intrigued, the scientists map these sequences, eventually realizing they correspond to mathematical constants or binary codes. The message might start simply, with universal mathematical principles before introducing more complex information. Over time, the civilization decodes the entire transmission, uncovering layers of knowledge embedded in the comet's chemistry. The masked broadcast theory also raises questions about communication across space and time. Unlike radio waves, which degrade over vast distances, chemical signatures remain stable and detectable even after millennia. This makes them ideal for interstellar messages, particularly for civilizations communicating across galactic scales. The use of universal physical constants ensures the message remains intelligible, regardless of the recipient's technology or language. What's known, 3I Atlas has an unusual chemical composition, with spectral signatures that deviate from typical cometary behavior. Observations during its perihelion revealed fluctuations in outgassing patterns that defy conventional explanations. These anomalies have sparked debate, with some researchers suggesting they could be evidence of deliberate modulation rather than natural phenomena. What's unknown? Is there a message hidden within it? The answer may lie in the data collected during perihelion. If the masked broadcast theory is correct, decoding the message requires analyzing subtle variations in 3I Atlas's chemical composition. Researchers are using advanced algorithms and machine learning to search for patterns, but the process is slow, and results remain inconclusive. The coma of 3I Atlas exhibits unusual abundance ratios of elements like carbon and oxygen isotopes. These ratios suggest artificial manipulation. Additionally, the timing and intensity of outgassing events appear to follow a non-random sequence, further supporting the hypothesis of intentional design. If these observations are evidence of a masked broadcast, it would be a monumental breakthrough in the search for extraterrestrial intelligence. Such a discovery would confirm advanced civilizations and provide insight into their communication strategies and technology. More importantly, it would validate the idea that interstellar messages can be embedded in celestial objects, opening new avenues for SETI research. What if 3I Atlas is just one of many such artifacts scattered across the galaxy? Advanced civilizations might have seeded the cosmos with these message comets, each containing a piece of a larger communication puzzle. Over time, as more of these objects are discovered and decoded, humanity could piece together a cosmic narrative, a story told by beings separated from us by unimaginable distances and timescales. This underscores the importance of continued observation and analysis, as each discovery brings us closer to understanding our place in the universe. The search for extraterrestrial intelligence is fundamentally a quest to determine if we are alone in the cosmos. The masked broadcast theory offers a tantalizing glimpse into how such communication might occur, using the universal language of chemistry and physics. As we unravel the mysteries of 3i Atlas, we edge closer to answering one of humanity's greatest questions: the possibility of contact with beings beyond our world. Part 16. The Decoy Shepherd Scenario. Are there microprobes hiding in the dust? The most sophisticated military strategies often employ decoy systems that capture enemy attention, while the real operation proceeds undetected through parallel channels. Applied to interstellar reconnaissance, this principle suggests a chilling possibility. What if 3i Atlas represents not the primary mission, but merely the conspicuous distraction designed to keep our telescopes busy while the actual payload achieves its objectives through entirely different means? The notion is not as far-fetched as it initially seems. Throughout history, military decoys have been used to great effect, from the Trojan horse of ancient Greece to the inflatable tanks and aircraft deployed during World War II, to mislead enemy intelligence. In the context of interstellar travel, where resources and opportunities are limited, the use of decoys becomes an even more attractive. Strategy. The decoy shepherd scenario proposes that 3i Atlas functions as an interstellar school bus rather than a lone explorer. Its primary mission involves drifting through our inner solar system while quietly dispersing a swarm of millimeter to centimeter microprobes disguised as ordinary comet dust. These microscopic payloads then spiral into carefully selected niches throughout our solar system: Earth Trojan points, lunar far-side craters, upper atmospheric layers where they can conduct extended surveillance operations using technologies too small for current detection methods to identify. The concept of microprobes is not new. NASA has experimented with microchip-sized spacecraft, such as the ChipSats, developed by the Breakthrough Starshot initiative, which aims to send gram-scale spacecraft to the Alpha Centauri system. If an extraterrestrial civilization has mastered such technology, it is conceivable that they could deploy it on an interstellar scale. The engineering requirements for such a strategy explain every anomaly we've observed in ways that natural explanations struggle to match. A decoy mission demands trajectory stability with near-zero net non-gravitational acceleration to keep deployment calculations simple and predictable. Any random kicks from asymmetric outgassing would scatter the microprobe swarm across unpredictable trajectories, defeating the precision required for targeted infiltration of specific orbital niches. Symmetric outgassing that cancels thrust vectors while maintaining vigorous activity serves dual purposes within this framework. It provides the cover story of natural comet behavior that satisfies most scientific observers while creating the stable platform necessary for controlled release of artificial payloads at predetermined times and locations. The precision required for such a mission is staggering. Consider the Voyager 1 spacecraft launched in 1977, which required a gravity assist from Jupiter and Saturn to achieve its current trajectory out of the solar system. For an interstellar mission to successfully deploy microprobes into specific orbital niches, the level of precision and control would need to be orders of magnitude greater. Observation: 3i Atlas has exhibited unusual behavior. Compared to other comets, its outgassing patterns are symmetric, which is atypical for comets that usually display chaotic, asymmetric venting. This symmetry could be a deliberate design choice to maintain stability during the deployment of microprobes. Additionally, the comet's trajectory has been remarkably stable, with no significant deviations that would suggest uncontrolled outgassing. This stability is crucial for the precise deployment of microprobes, ensuring they reach their intended targets without scattering randomly. Interpretation: the symmetric outgassing and stable trajectory of 3I Atlas could be engineered features rather than natural phenomena. If the comet is indeed an interstellar decoy, its designers would have prioritized stability and control to ensure the successful deployment of microprobes. The absence of random outgassing events supports the idea that the comet's behavior is carefully managed, possibly through advanced propulsion systems or internal mechanisms that regulate gas release. Speculation: if 3I Atlas is a decoy, the microprobes it deploys could be equipped with advanced sensors and communication systems. These probes might be capable of transmitting data back to their origin point, providing valuable intelligence about our solar system. The possibility of such technology raises profound questions about our place in the universe and the potential for extraterrestrial surveillance. It also highlights the need for continued observation and analysis of 3I Atlas to uncover any hidden payloads or anomalous behaviors. What's known: 3I Atlas is venting gas and dust. What's unknown? Are there microprobes hidden within it? The answer may lie in the data collected during perihelion. However, the challenges of detecting microprobes are significant. Current telescopes and sensors are designed to observe macroscopic objects, not millimeter to centimeter devices. The microprobes, if they exist, would be indistinguishable from ordinary comet dust, making their detection exceedingly difficult. Advanced techniques such as spectroscopic analysis or radar imaging might offer clues, but even these methods have limitations. The search for microprobes would require innovative approaches and possibly the development of new technologies specifically designed for this purpose. The implications of the decoy shepherd scenario are far-reaching. If 3I Atlas is indeed an interstellar decoy, it suggests that an extraterrestrial civilization has not only mastered interstellar travel, but also developed advanced stealth and surveillance technologies. This raises questions about their intentions and the potential for future contact. Are they observing us out of scientific curiosity, or do they have more strategic goals in mind? The possibility of extraterrestrial surveillance also underscores the need for international cooperation in monitoring and responding to such phenomena. If microprobes are detected, it would mark a historic moment in human history, confirming the existence of extraterrestrial intelligence and opening the door to new forms of interstellar diplomacy. In the meantime, the mystery of 3I Atlas continues to captivate scientists and the public alike. As we gather more data and refine our observational techniques, we may uncover the true nature of this enigmatic object. Whether it is a natural comet or an interstellar decoy, the study of 3I Atlas offers valuable insights into the possibilities of interstellar travel and the potential for extraterrestrial life. The journey of discovery is ongoing, and each new piece of evidence brings us closer to understanding the cosmos and our place within it. Part 17. Closing Reflections. What does 3I Atlas tell us about the universe? In the end, 3I Atlas forces us to confront a fundamental paradox that cuts to the heart of how we understand the physics governing small bodies in space. Here is an object displaying vigorous activity, visible outgassing, evolving tail structures, rising production rates of multiple chemical species, yet producing little to no measurable acceleration according to the precision astrometric measurements that form the foundation of modern orbital dynamics. This contradiction between apparent cause and absent effect represents either a significant gap in our theoretical understanding or evidence for phenomena that operate outside conventional physical frameworks. The absence of detectable acceleration, despite the object's clear activity, has puzzled astronomers who expected to observe the rocket effect caused by the ejection of material. This effect, which has been observed in other comets, typically results in a slight but measurable change in the comet's trajectory. For example, Comet 67P Churyumov-Gerasimenko, studied by the Rosetta mission, exhibited non-gravitational accelerations of up to 0.3 millimeters per second squared, directly linked to its outgassing activity. In contrast, 3I Atlas shows no such deviations despite comparable levels of activity. The lack of acceleration is particularly striking when considering that 3I Atlas releases an estimated 20 kilograms of material per second during its peak activity, equivalent to the mass of a small car every hour. This sustained outgassing should, by conventional models, produce a noticeable change in trajectory, yet no such change has been observed. The current best-supported scientific picture places 3 Atlas firmly within the category of natural phenomena, albeit at the extreme edge of what we've previously observed or predicted. This interstellar visitor carries the chemical fingerprints of formation in an environment unlike our solar system, possesses unusual composition dominated by carbon dioxide rather than water, and exhibits the mysterious nickel without iron abundance pattern that challenges conventional models of metal emission from comet nuclei, its apparent mass concentration and symmetric outgassing. Patterns provide plausible natural explanations for the missing non-gravitational acceleration that has captured scientific attention worldwide. Detailed spectroscopic analyses have revealed that 3I Atlas contains unusually high levels of carbon-bearing molecules, such as carbon monoxide, CO, and carbon dioxide, CO2, which are rare in solar system comets. These compositional anomalies suggest that 3I Atlas formed in a colder, more carbon-rich environment than the comets we are familiar with. Additionally, the object's outgassing behavior appears to be highly symmetric, with material ejected uniformly across its surface. This symmetry may explain the lack of detectable acceleration, as balanced outgassing would not produce a net force on the object. The symmetric outgassing is particularly intriguing because it suggests that 3I Atlas may have a highly uniform surface composition, unlike many solar system comets, which often exhibit localized jets of material from specific active regions. This uniformity could be a clue to its formation history, indicating a slow and steady accumulation of material in its parent system. Yet, acknowledging the spark of anomaly hunting that drives scientific discovery, we must recognize that 3I Atlas has already expanded our understanding of what comets can be, regardless of whether future observations confirm. Natural or artificial origins, the object has forced improvements in theoretical models, observational techniques, and analysis methods that will benefit the study of small bodies throughout our solar system and beyond. It has demonstrated the value of rapid response observational campaigns and international cooperation in extracting maximum scientific return from brief encounters with interstellar visitors. The study of 3I Atlas has led to advancements in computational modeling of cometary outgassing, with researchers developing new algorithms to simulate complex gas dynamics under extreme conditions. These models have been shared globally, enabling scientists to better predict the behavior of both interstellar and solar system comets. For instance, the development of adaptive mesh refinement techniques has allowed researchers to simulate the outgassing process with unprecedented resolution, revealing intricate patterns of gas and dust interactions that were previously unobservable. The educational and cultural impact extends far beyond professional astronomy. 3i Atlas has captured public imagination in ways that highlight both the wonder and complexity of scientific investigation. It illustrates how genuine research operates at the boundaries of knowledge, where uncertainty and speculation play essential roles in advancing understanding while maintaining appropriate standards for evidence and proof. The discovery of 3i Atlas has inspired countless educational programs, public lectures, and media coverage, introducing millions of people to the fascinating world of interstellar objects. School children have written essays about the object, artists have created visual interpretations of its journey, and amateur astronomers have contributed valuable observations to professional research. The amateur astronomy community, in particular, has been instrumental in tracking 3i Atlas's brightness variations over time, providing data that has helped refine models of its rotational behavior. These contributions underscore the democratization of science, where citizen scientists play a critical role in expanding our collective knowledge. The object serves as a perfect case study in how science approaches potentially revolutionary discoveries. With excitement tempered by skepticism, curiosity balanced by rigor. Looking toward the immediate future, the perihelion passage scheduled for late October 2025 represents our final opportunity to resolve the central mysteries surrounding this enigmatic visitor. Enhanced solar heating might trigger new activity patterns that finally produce detectable acceleration signatures, confirming natural explanations through direct observation of the rocket. Effect in action. Alternatively, persistent dynamical stability in the face of intensified outgassing would deepen the anomaly and strengthen arguments for exotic explanations. During its perihelion passage, 3i Atlas will be subjected to temperatures exceeding 300 degrees Celsius, potentially releasing deeply buried materials that could provide new insights into its composition and history. These materials, which may have been locked beneath the salt surface for billions of years, could include rare isotopes or complex organic molecules that offer clues to the object's origins. Spacecraft observations from Mars orbiters and other deep space missions could provide unique viewing angles impossible to achieve from Earth-based telescopes. High-resolution imaging might finally resolve the nucleus itself, eliminating uncertainties about size, shape, and surface properties that currently limit our ability to distinguish between competing theoretical models. Precision spectroscopy during peak activity could reveal isotopic signatures that definitively establish natural versus artificial material sources. For example, the Mars Reconnaissance Orbiter's HiRISE camera could capture images of 3i Atlas with a resolution of up to 0.3 meters per pixel, allowing scientists to study its surface in unprecedented detail. Additionally, the ESA JAXA BP Colombo mission, en route to Mercury, could use its onboard spectrometers to analyze the object's composition as it passes through the inner solar system. Such observations could detect trace elements or unusual compounds that are not visible from Earth, providing additional evidence to support or refute existing hypotheses. The broader implications ripple outward from this single object to encompass fundamental questions about the prevalence of life and intelligence in the universe. If 3i Atlas ultimately proves natural in origin, it expands our catalogue of exotic phenomena that operate within known physical laws while challenging our ability to predict and explain natural processes. If future evidence supports artificial origins, it would represent the most significant discovery in human history, confirming that we share the cosmos with other technological civilizations. The search for extraterrestrial Intelligence, SETI, has long been a subject of scientific inquiry, but the detection of an artificial interstellar object would transform it from a speculative endeavor to a tangible reality. Such a discovery would galvanize global efforts to detect and study other potential signs of alien technology, from radio signals to megastructures. The Breakthrough Listen initiative, for instance, has already begun targeting 3i Atlas with sensitive radio telescopes, searching for any techno-signatures that might indicate intelligent design. The statistical context becomes crucial for understanding the significance of any conclusion we ultimately reach. 3 confirmed interstellar visitors in 8 years, with 2 displaying highly unusual characteristics, suggests either remarkable coincidence or systematic differences between objects formed in our solar system and those arriving from interstellar space. The upcoming Vera Rubin era promises to transform this tiny sample into comprehensive population studies that will reveal whether anomalous behavior represents rare exceptions or common characteristics of interstellar visitors. The Vera Rubin Observatory, expected to begin full operations in 2024, will scan the entire visible sky every few nights, detecting thousands of moving objects, including interstellar visitors. This vast dataset will allow scientists to compare the properties of interstellar objects with those of solar system bodies, potentially uncovering fundamental differences in their formation and evolution. The observatory's Legacy Survey of Space and Time, LSST, is projected to catalogue over 10 million solar system objects in its first decade of operation, providing an unparalleled database for comparative studies. International cooperation and technological advancement will prove essential for maximizing our ability to study future discoveries. The brief visibility windows of interstellar objects demand rapid telescope allocation, immediate spectroscopic follow-up, and real-time analysis capabilities that push current observational infrastructure to its limits. Success requires sustained investment in detection systems, analysis methods, and theoretical frameworks capable of distinguishing between natural variations and genuinely extraordinary phenomena. The Global Telescope Network, a proposed international collaboration, aims to coordinate observations across dozens of telescopes worldwide, ensuring that no fleeting interstellar visitor goes unstudied. Such a network would enable continuous monitoring of objects like 3i Atlas, capturing their behavior in real time and providing scientists with the data they need to unravel their mysteries. This network could also facilitate rapid follow-up of transient events such as sudden outbursts or fragmentation, which could provide critical insights into the internal structure of interstellar objects. Perhaps most importantly, 3i Atlas reminds us that the universe retains the capacity to surprise us. Despite centuries of astronomical observation and decades of sophisticated space missions, we continue encountering objects and phenomena that challenge our theoretical understanding and force us to expand our conception of what's possible. This intellectual humility, the recognition that our knowledge remains incomplete and our theories remain provisional, represents the essential mindset for conducting honest scientific investigation at the frontiers of discovery. The history of astronomy is filled with unexpected discoveries that have reshaped our understanding of the cosmos, from the realization that the Earth is not the center of the universe to the detection of exoplanets orbiting distant stars. 3i Atlas joins this long tradition of paradigm-shifting objects, pushing us to question our assumptions and explore new possibilities. The discovery of pulsars in the 1960s, for example, initially baffled astronomers who struggled to explain their rapid, regular pulses of radio emission. It was only through sustained observation and theoretical innovation that scientists recognized these objects as rapidly spinning neutron stars, fundamentally altering our understanding of stellar evolution. Whatever 3I Atlas ultimately proves to be, natural oddball or artificial artifact, it has already secured its place as the most scientifically important interstellar visitor since Oumuamua and Borisov. Not because it provides definitive answers to the questions that drive our curiosity about life and intelligence in the universe, but because it forces us to ask better questions, develop better tools, and maintain better standards for evaluating evidence that might transform our understanding of our place in the cosmos. The study of 3I Atlas has led to the development of new instruments, such as the Interstellar Object Chaser, IOC, a proposed spacecraft designed to rendezvous with future interstellar visitors and study them up close. Such missions would provide unprecedented insights into the nature of these enigmatic objects and their implications for our understanding of the universe. The IOC concept envisions a fleet of small, agile spacecraft equipped with advanced sensors and propulsion systems, capable of intercepting interstellar objects within weeks of their discovery. These spacecraft could deploy miniature landers or drones to explore the surfaces of these objects, collecting samples and performing in situ analysis. The mystery continues. The observations continue. And our quest to understand these cosmic messengers carries us ever deeper into questions that probe the very nature of reality itself. In the end, that journey of discovery might prove more valuable than any single answer we uncover along the way. The search for understanding is a never-ending process, driven by our innate curiosity and desire to make sense of the world around us. 3I Atlas, with its puzzling behavior and elusive nature, embodies this quest, challenging us to push the boundaries of our knowledge and explore the unknown with open minds and unwavering determination. As we continue to study this remarkable object, we are reminded of the vastness of the cosmos and the limitless possibilities it holds. The universe is full of mysteries waiting to be unraveled, and 3I Atlas is just one step on our journey to unlock its secrets. Observation. The scientific community's response to 3I Atlas exemplifies the interplay between observation, theory, and technological innovation. As our instruments and methods improve, so too does our ability to detect and analyze interstellar objects that were once beyond our reach. The ongoing investigation of 3I Atlas underscores the importance of sustained investment in research infrastructure, international collaboration, and public engagement. In the pursuit of knowledge, interpretation, the enigmatic nature of 3I Atlas highlights the tension between the familiar and the unknown in astronomy. While its behavior challenges conventional models, it also offers an opportunity to refine and expand our understanding of cometary processes, interstellar environments, and the potential for life beyond our solar system. Whether natural or artificial, 3I Atlas represents a turning point in our exploration of the cosmos, pushing us to confront the limits of our knowledge and the possibilities that lie beyond. Speculation. If future observations reveal that 3I Atlas is indeed an artificial object, the implications for humanity would be profound. Such a discovery would not only confirm the existence of other technological civilizations, but also raise fundamental questions about their nature, intentions, and the role of intelligence in the universe. It would compel us to reconsider our place in the cosmos and the potential for interstellar communication, travel, and cooperation. Conversely, if 3i Atlas is ultimately shown to be a natural object, its unique characteristics would still challenge our understanding of planetary formation and the diversity of worlds in the universe, inspiring new theories and avenues of research. In either scenario, 3i Atlas serves as a reminder of the boundless potential of scientific inquiry. It embodies the spirit of exploration that has driven humanity to push the frontiers of knowledge, from the earliest stargazers to the modern era of space exploration. As we continue to study this remarkable object, we are not only unraveling the mysteries of a single interstellar visitor, but also deepening our understanding of the universe and our place within it. The journey of discovery is ongoing. And 3i Atlas is a beacon guiding us toward new horizons.